Hello everybody, good morning or afternoon or evening depending on where you are. Obviously I'm currently in Manchester, stuck in my apartment, and so everybody at IPEC is working from home. So what we thought we'd do is a series of webinars and product discussions. So we're going to do more in the future for sure, and what we thought we'd do is do series of webinars, talk a little bit about PD, a little bit about IPEC products, take any questions from people, because obviously at the moment we're not able to get out and get to sites and discuss in person. So hopefully you'll find it sort of useful, hour to an hour and a half, depending on how we get through the material. And if you have any questions, feel free to add them to the comment section and put your company name and your name as well, so that we know who you are, and then we can respond appropriately to your questions. There's a delay from what I'm speaking now to it going live on YouTube. The delay is about 10 to 15 seconds. So excuse me if I take a bit of time to get to your question, but I will see them all and I will sort of get around to them as we go. Feel free to ask questions during, and I'll also do a bit of time at the end for any questions that we have at the end there. So, okay, without further ado, I suppose let's get started with the presentation. So throughout the presentation, you'll still see me in the bottom left-hand side, and I might move myself around depending on if I get in the way of the content. So yeah, we'll cover a little bit about IPEC, about our company, our clients, a bit of timeline on our products, PD theory, so looking into what PD is, why it occurs, and then we'll look really at how you can detect PD, the different types of sensors that can be used to detect them, and then we'll jump on a little bit about IPEC products and how we incorporate those sensors into our range of products. So if you don't know me, I'm Carl Eastham. I'm the Business Development Director at IPEC, so I've been with IPEC for about 13 years. My focus of work, if you like, is working with our distributors around the world, working with our end users, to basically find solutions to the problems that they have. So applying different online PD technology in different environments around the world is mainly what my focus is on. Okay, so IPEC has been around for about 25 years. We were founded in 1995 from the University of Manchester. We're still based in Manchester. That's our head office, that's our headquarters. And our focus as a business is detecting PD online in medium voltage, high voltage, and extra high voltage networks. All we do as a business is partial discharge, and we only do online PD, so detecting PD during normal operation of the equipment. IPEC very specifically is quite well known for our ability to differentiate PD from background noise. Online partial discharge, there is a susceptibility of noise interference, and that's one of the biggest problems or the biggest known issues in the industry. And so throughout our product range, in our more advanced permanent monitoring systems or more simpler handheld instrumentation, we make sure there's a function to differentiate PD from noise throughout the range. And I'll come into some details about that as we go through the presentation. But that's what we're quite well known for. So it means that we've got monitoring systems and installations around the world, including in particularly very high noise environments. Tends to be a good market for us, or where customers are very interested in our products because of that ability to differentiate between the two. Our PD monitoring system, which is our history of the product range, if you like, so where we started, our core technology is our permanent monitoring solutions. That's one of the world's most popular systems, installed in more substations and more assets than anybody else, I think. Over 6,000 cable circuits monitored, over 7,000 switchgear, 24 hours a day live, so customers can see the PD activity on the network and respond to it appropriate. We've got billions of individual PD events. We've got hundreds of millions of phase resolved partial discharge patterns, so quite a lot of data collected by our systems, which helps us build from our monitoring system into our other solutions and experience as well. Because of that sort of university background, we still have and hold a very strong research and development side to the business. So we're constantly innovating, constantly developing our products to ensure sort of a continued innovation and to make sure that our solutions are applicable to the market. In these days, the markets change quite quickly. The requirement from customers can change quickly in the solutions, particularly with this sort of digitization requirement and smart smarter networks, and you know, a lot of the work now is about integrating data from systems into customer data networks, as you guys will be familiar with. So this is IPEC's footprint, if you like. We are based in Manchester, that's the head office. We've got a couple of offices in the United Kingdom. And then around the world, we work with a series of partners or distributors. If I just move myself there. We work with a series of partners or distributors so that we have a local contact, a local connection for our clients in their territory. Outside of Europe and the UK, which is obviously where we're based, we're quite active in the Middle East and the Far East. The Far East, actually, Asia makes up the majority of IPEC's business, probably around just over 50% of our business. A lot of it in Southeast Asia, which is quite a growing market base for IPEC, so we do a lot of activity around there, as well as East Asia in general. So we're very active in that region. We're a network of distributors, and we're also very active. We're always out in that area as well. Some key clients then. I'm not going to go through the individual clients, but we work with, I suppose the reason for this slide is just to show that we work with a combination of both large utility networks, large energy network operators, electricity network operators, and also smaller private networks. So a lot of the focus particularly in the, say, South Korea, for example, the high-tech manufacturing side of the world, we do a lot with private networks because of that security of supply, which is required and very critical for the production of assets. On the other side, we also work with large distribution networks, looking at large-scale monitoring across large regions. So Hong Kong, for example, on Hong Kong Island, Hong Kong Electric, every 11 kV primary substation has one of IPEC monitors installed, looking at every single feeder cable and every single switchgear. So we cater for the small networks, and we also cater for the very large networks, and our systems are actually very well designed to cater and versatile for small or large installations as well. So I'll just put my head back in the corner, and then we'll move on to the next slide. So a little bit of a timeline then. Mainly this is a product timeline I wanted to focus on. So IPEC was founded in 1995. At first we launched sort of the OSM ST1, which was at the time very innovative in terms of online PD detection. A portable online PD detection tool enabled you to view PD in that PRPD mode. Shortly afterwards, we launched the monitoring system, the OSM monitoring system, which at the time was the world's first permanently installed PD monitor with a web interface. So you were able to connect to the monitoring system, dial in and view PD data. And of course, in 22 years ago, in 1998, that was quite a rare thing to do. The main focus of the equipment was ultrasonic, so mainly focused on looking for defects in cable terminations, but a very useful device. Probably the biggest step in IPEC's evolution was in 2001, we started a collaborative relationship with London Electricity, which then became EDF Energy and is now known as UK Power Networks. And what we did there really is we focused on taking the technology that we had, the technology, that basic technology, and moving it into something more applicable to large-scale networks. So London Electricity obviously ran the network in London. The biggest problems there were PD and underground cables. So we were at the forefront of that really, and turning our monitoring system into something that could be installed across the whole of the London network, with HFCT sensors monitoring underground cables live and online. So we installed those systems, and the output of that really was a very robust online monitoring system that we called the ASM, which is now still used around the world. Obviously, it's gone through many iterations and many developments into what it is today. So we launched a range of instrumentation and portable tools as well. So along with the permanent monitor, we realized that customers did want to see portable equipment. So taking some of that technology, taking some of that knowledge, from our permanent monitoring systems and putting it into portable equipment. So the ASM, this is what the ASM looks like today. It's a 19-inch rack based monitoring system. Like I said, it's gone through a number of iterations, and I'll come on to a little bit more detail about the ASM a little bit later on. Then skipping through the other products, basically what we have now and what we launched over the last sort of 10 years, if you like, is technology and equipment complementing the permanent monitoring systems, instrumentation focused on medium voltage switchgear, and then with the permanent monitoring system, which originally was focused on, of course, the application of medium voltage, it then expanded into EHV, looking at GIS, with UHF sensors, and also the PD alarm, which is more for smaller and secondary substations as well. So we've got sort of a full product range now across different solution applications, instrumentation and permanent monitoring, as well as different network applications in terms of transmission and distribution side of things. So this is our summarized product range, if you like. So on the PD monitoring side, we have two what we call ranges of systems. The first one is the PD alarm. So that's a small device. I'll come into a little bit more detail about how it works. So a small PD alarm, which is focused on mainly on medium voltage switchgear monitoring. It's essentially a bit like a handheld instrument, but focused on small, quick applications. Then there's the ASM series, of which there is a number of different monitoring systems within that. But the functionality of the monitors are all fundamentally the same. The way they process the data, the way they save the data, the way they display the data to the end user is identical. The difference being the housing, the package, how we build the product to make it more applicable for different environments. And I'll come on a little bit more information later on that. Then on the right hand side, we've got the instrumentation. So our online PD instruments, PDSGS, PD detector and PDSG1. The main difference between these devices is really the type of data you're getting out, how you're getting it out and how you're processing it. So the PDSGS is the first line, very simple handheld device for quick spot testing of assets. The PD detector has the same functionality as the SGS, but also allows you to view more advanced data, record it onto a mobile phone, stream it onto a mobile phone, and also save it into the database against particular assets as well. So it gives you that connectivity in the range. And then finally, the PDSG1 is used to pinpoint and locate problems in the switchgear. So after you've maybe detected problems with either the PDSG1 or maybe the PDSGS or PD detector, then the PDSG1 can be used to pinpoint the problem online in the switchgear. And it's just worth re-emphasizing that at the moment. Online PD is what we do. So we don't do any offline testing or offline equipment. Of course, we do recommend a combination of things in a sort of condition-based maintenance practice. But as a business, IPEC, we only cover the online partial discharge world. So all of our products are used online. Okay, so along with our permanent monitoring systems, of course, we have a range of, put myself up to the top left at the moment. We have a range of associated services, as you would imagine. So first is data analysis. So when customers have our equipment, we understand our equipment is not always the easiest thing to use. Online PD, the interpretation of online PD data can be tricky. Particularly if customers are quite new to this sort of environment. And so we do offer data analysis services. We're happy to analyze customers' data for them. We're happy to produce reports. We're happy to support in that regard with our PD experts. The other side then is data hosting. With our permanent monitoring systems, we can host data in our data center in Manchester. So rather than the customers requiring their own servers on site, we can host it in IPEC in Manchester. However, it must be pointed out that we can also install a server on the customer site. With all of our monitoring systems, we do not require customers to send data to IPEC in Manchester. Our systems are designed to be completely closed system, if you like. With training, customers will be able to host the data, they'll be able to interpret the data, not a problem. Free support is a key thing for IPEC. One of the things is we understand that even with some training, customers, when they first come across a PD, they're going to want a second opinion possibly to decide whether they should be taking action on a particular asset. And so before shutting the asset down, before spending the money, if you like, on attempting a repair of the asset, we offer a free of charge support service. So customers are welcome to email IPEC with data, email IPEC with the output of the systems, and just ask for a recommendation from IPEC. Ask us to review some existing reports. We're happy to do that as well. On the on-site services then, out in the field, of course, we do a range. We do PD testing, training courses, and installation and commissioning. All of these three solutions really are a combination with IPEC directly or with our partners. So we understand that actually it can be quite costly to get an engineer from the UK, for example, to come out to different parts of the world to conduct paid for PD testing or installation and commissioning, etc. So we work with our partners, and in each country we have a different solution to these problems. A lot of the training courses are held directly by IPEC in different parts of the world. But of course, installation and commissioning and some PD testing is done on behalf of us with our clients. But we're very flexible with on-site requirements as well. Okay, if I look at the sensor side, so I'll just move myself completely out of the way there. Okay, so if we look at the sensors, basically, I'll go into detail a little bit about how these sensors operate, but online PD, there's a sort of industry standard of the types of sensors that are used for online PD detection, and of course IPEC conforms to those standards, and so many people familiar with PD will be familiar with these sensor types. All of these sensors are made by IPEC, but we have a range of different sizes and shapes of different sensors and devices depending on the application. I'll come into a bit more detail about how each sensor operates later. So research and development here at IPEC, continually developing. We do work with other partners to make sure we're staying on top of the latest technical innovation. Of course, as you'd imagine, there's different companies around the world, there's different expertise. So we work very closely with the university, we work very closely with other partners to make sure that our products are meeting the current standards, the current requirements as well. All of IPEC systems and products are made by IPEC or IPEC intellectual property. So everything we do has been designed by IPEC. Some products we manufacture in-house, so particularly low volume products or very complex products we manufacture in IPEC in Manchester. However, other products we will subcontract the manufacturer, so the high volume products like the handheld instrumentation, but every product is still made in the United Kingdom. So, but it's all IPEC property and IPEC design. So everything you're buying, we do not buy and sell any components. We make them ourselves. Okay, so now comes to the fun bit of the presentation, and I definitely need a sip of tea for this. Okay, so I don't want to go into partial discharge theory too much, and in fact in future sessions I may do some very detailed and dedicated partial discharge theory sessions. However, what I wanted to do is give a brief overview of partial discharge. There is a wealth of knowledge out there, and equally if anyone's got any questions afterwards, feel free to ask. But partial discharge is an electrical discharge that doesn't completely bridge the space between two conducting electrodes. Essentially, you know, if you've got a conductor and you've maybe got another phase, or you've got the earthing point, so two electrodes essentially, a partial discharge is a discharge occurring in between those, so not completely bridging the gap, but occurring at some point in between them, and it's a point of electrical stress. It's a point where PD is occurring. I'll go through it in a moment. So PD can occur face to phase or from phase to earth. So depending on where the defect is, where the problem is in the network, depends on where it occurs. But it can basically occur where you can get a point of electrical stress. So naturally that can be between two phases, heading in different directions if you like, or it can be between phase and earth. It can be in gas-filled voids in solid insulation. It can be in bubbles in liquid insulation, or around electrodes in air, which is sometimes can be corona, but can also be surface tracking. So on switchgear, so IPEC tend to focus it on switchgear and cable. Naturally, on switchgear, you tend to get, we classify really as two types. So the first one is surface tracking. So that's when you've got maybe contamination on the outside of an insulator. So you'll get some surface tracking activity, so electrical tracking over a contaminated insulator. The other type is internal discharge. So that's where you've got a defect inside a solid insulation. Maybe you've got a crack, maybe you've got a gas-filled void problem from manufacture, or like I said, a crack from damage of insulation, and that's an internal discharge. Now, as you can imagine, with both of those, as you know, with both of those defect types, they can occur across different parts of the network. So they can occur anywhere within a switchgear, if you like, because obviously you've got high voltage running throughout the switchgear, you've got insulation throughout the switchgear, and any component of that insulation could be damaged, which could cause a partial discharge to emerge. Surface tracking is most commonly probably found inside cable terminations, but it can of course occur on bushings and any other sort of where there's a high voltage and then a neighbouring open surface. Internal discharge can occur anywhere inside cable terminations, if they're solid terminations, inside the end of cables, inside circuit breakers, inside CTs, VTs, so all different components of the equipment. When it comes to underground cables, the two areas that we see PD activity really, joints and accessories, are by far the most common place to see PD activity. In XLPE systems, so modern cable systems, probably 99, if not 99.5% of PD will be inside the joints. Manufacturing processes now are very accurate, so pure cable PD is very unlikely, and if it occurs, it's probably detected at the time of commissioning or detected at the time of manufacture even. But in the joints and accessories, that's where we're going to find the problems in cable networks. So 99% of PD will be inside joints and accessories. You do get PD in the pure insulation. It can happen. It's much less common with XLPE, like I say, but if you're looking at oil and paper cables, so the older cable types, we still have a lot of that in the United Kingdom, for example, you can find a lot of PD occurring in the oil and paper. However, it's not necessarily always a concern, and I'll come on a little bit about that later. Okay, so the next few slides really go through the mathematical side of PD and why they occur. This presentation will be uploaded onto our YouTube account for permanent review anyway, so you're welcome to look back at these slides and this presentation. But I suppose what I wanted to really focus on here is just the fundamental principles of PD and where specifically it's occurring. So I'm not going to go through too much of the mathematics, because in the UK it's still 8:27 and I have a rule not to do any maths before 9 AM. So I'm not going to go into too much detail, but I will highlight the sort of main impact. So if we take our sort of ideal case, if you like, which is a solid piece of insulation with a perfect defect inside that insulation. Actually, what we're looking at here, why a PD occurs, is not because there is, say, a gas-filled void. It's not because there is gas within the insulation that's causing a lower insulation level. The problem is that the combination of your XLPE or your polymer, your traditional insulation, with a different material, with an air gap, causes an area where you can get an increased point of stress. So the easiest way to explain that is if I look at this slide here. So the breakdown strength of air is 3 kV per millimeter. So over a 20 millimeter air gap, that could withstand a 60 kV insulation. The breakdown strength of this polyurethane, this XLPE essentially, is 10 kV per millimeter, so over a 20 millimeter insulation that could handle 200 kV. However, the problem is that because you've got a combination in our defect here, because you've got some XLPE, then you've got a gas-filled void or an air gap, and then you've got more XLPE. What that means is instead of a uniform dissipation of the energy from the conductor, instead of a uniform dissipation, you get a localized area of capacitance, you get a localized area of stress. So what it means is as the energy in the power cycle increases, the stress very specifically at that defect point increases also. And as that stress increases within normal working voltages, you will get a very small low energy breakdown across that defect. So it must be noted that breakdown is at the defect. It's not across the whole space, if you like. It's just very locally at that defect, and it's a very low energy breakdown. You wouldn't notice it in your electricity network. But what the problem comes from, it acts within working volts. So if we did run through the mathematics, what we would find is that the breakdown strength in this example here is 17.25 kV. So what that means is, whereas, like I said, air would normally withstand 60 kV, the XLP on its own can withstand 200 kV. A combination of the two, this very small air gap, means that at 17.25 kV you get a very small discharge occurring very locally just inside this defect. And so that's what a partial discharge is. It's partially discharging, it's discharging inside that defect. Now the discharges themselves are very low in energy, but it is that repetition in that localized area over time which causes the problems. So as we said, at 17.25 kV is when there's a breakdown, and so this diagram is a little bit complicated, but if you imagine this line here as the line at which the breakdown occurs, so this is our 17.25 kV charge, if you like. What happens is, as the energy in the power cycle is increasing, so if my laser pointer is much easier to demonstrate this. So as the energy in the power cycle is increasing, the stress across that defect is also increasing until eventually it reaches that breakdown point, and then it indeed breaks down. Now the energy in the power cycle is still increasing, and so again we'll get a recharge and a breakdown, recharge and breakdown. So what happens is, on the rising edges of the power cycle, the positive go inside and then the negative go inside, we get an increase in charge, a discharge, increase, discharge, increase, discharge, and then we flip to the negative side, and then we get an increase, discharge, increase, discharge. So what it means is PDs have a very specific pattern in the power cycle. So as the energy in the power cycle increases, discharge will occur both on the positive side and the negative side of the power cycle. So on the right hand side is images that people might be quite familiar with. This is called a PRPD, phase resolved partial discharge, and it's PD patterns in the power cycle essentially. It's one of the tools that is used within a lot of PD equipment, within a lot of instrumentation, to help you decide if the signal you're seeing is from a genuine PD source or from a noise source. It's this distinctive pattern. So here we can see, all we're looking at here is raw data, and each one of these markers is a PD location, but we can very clearly see PD occurring in the power cycle here. So PD, rising edge of the power cycle, falling edge of the power cycle. This one's flipped around the other way, but it's the same thing, rising edge of the power cycle, rising edge of the power cycle. So as the energy is increasing, that's where partial discharge is increasing. Now, of course, this one here on the bottom right hand side is a condensed PRPD, which is quite common as well. It's one power cycle on top of another, so it's quite common of instrumentation to have that functionality. So instead of looking at a single power cycle where there may only be one PD, what you want to do is record data over a period of time, put them all together so that you can see this sort of pattern in the power cycle. Okay. So like I said, every time these small PDs occur, they're very, very low in energy, but they're very localized and they're very repetitive. So the defect point is very small, which means that's why they're very localized, but they're very repetitive over time, occurring multiple times per power cycle. Partial discharge activity doesn't vary between power cycle to power cycle, but it can vary over the day, it can vary over the year. So PD activity shouldn't be viewed as something that only occurs once every 20 power cycles, for example. PD is generally either occurring or not occurring. And generally, if there is a variation with load, that could be a variation throughout the day, or it could be a variation throughout the year. And what you generally find is not so much that PD occurs and doesn't occur. What you'll find is throughout the year or throughout the day, you'll get sort of high PD and low PD. So you'll get a variation of the level of PD, if you like. Regardless, those individual PDs then, they cause a combination of mechanical, thermal and chemical damage, so that over time, basically the defect that was started maybe from an installation problem or a manufacturing problem or some damage on the switchgear, the defect will slowly get worse over time until eventually there will naturally be a catastrophic failure of the equipment. How that damage propagates, or how that damage progresses. If you imagine in solid insulation, it's quite well known. Electrical tree will form. So over time, the physical damage to the insulation will form an electrical tree, until eventually the electrical tree is so large that the insulation can no longer survive the energy coming from the conductor. Surface tracking, if it's on outside of insulation, you get surface tracking, and generally what you'll see is this sort of carbonization on the outside of your equipment, which is evidence. You also see sort of white pitting as well, so evidence of that sort of surface tracking occurring, of PD occurring on the outer surface of equipment. So consequences of PD, first one is of course cable failure. If you've got a failure inside a underground cable, you'll see a loss of supply, you'll see an unplanned outage, increased CI and CML. CI is a UK measurement, customer interruptions. CML is customer minutes lost. Of course, every country around the world has a similar measurement criteria, basically looking at the impact of the power failure on where the supply is, so whether that's customers or whether that's industrial side of the business as well. So customer interruptions, customer minutes lost, and of course the failure point must be found. So naturally you need to find where that cable has failed with fault location technology in order to then conduct the repair to bring that system back online. Now with underground cables, that can be very problematic depending on where the cable actually falls. Last minute requirements, in London for example, we can get a 24-hour repair order, emergency repair, quickly shutting down a road, digging the road and repairing the cable. Still very costly, still very inconvenient, if you like, for the wider application. Cables aren't too bad though. Quite a lot of cable networks have redundancy, so a failure of a cable means you can often reconfigure the network. If it's a ring configuration, not a problem. If it's a radial network, that's where the problem comes in, because of course a cable failure is then a loss of supply until that cable is fixed. On the switchgear side of things then, this is quite a dramatic picture. On the wall here, this is actually compound from the cable termination. So this is a compound filled cable termination. This is from London, a picture we took in London. Compound filled cable termination. This is the opposite wall, so it's not carbonization from a large fire or something, even though it looks like that. But it is quite a dramatic picture that I like to use so to emphasize the first point, which is when you have switchgear failure, of course, the first problem is safety implications. So within that substation, you may have other engineers working, and so safety is the number one problem. When a switchgear fails, it's quite dramatic, and it can be quite damaging to anybody nearby. The other problem is collateral damage. So not only will that main switchgear be damaged, but it could also damage neighbouring equipment and neighbouring components within your substation. Major disruption, switchgear failures are very costly. They take quite a lot of time to repair, and whilst they are being repaired, of course the reliance or the redundancy is gone. So most substations have two sides to the bus bar. If one fails, then one bus bar is shut down while a repair is conducted. It means your redundancy is completely gone, relying on one side of the substation to operate the whole network, and it can be very, very expensive and disruptive. Okay, so now I want to come on to the different parts of the network and what sensors we use to detect PD. Okay, so like I mentioned earlier, the PD sensors that are used across the industry. So what you'll find is that other PD manufacturers will use the same type of sensors. And although, of course, I would claim that these sensors are the best sensors manufactured in the world, and of course I would be correct in that assumption, fundamentally everybody uses the same type of sensors, and it's not necessarily so much the sensor, although the design and the characteristics are very important. It's not so much the sensor, but it's more important is what you do with the data output. So HFCTs are relatively simple electrical devices, but it's what you do processing that data output which really makes the difference. And so that's applicable to all of our sensors, HFCTs, TEVs, ultrasonic sensors. In and themselves, they're very simple devices. The concepts are very simple. The sensor design is important but not critical, and what is critical really is what you're doing with the process, how you're processing the data afterwards. So for underground cables, we use a HFCT, high frequency current transformer, and that HFCT, they come in different shapes and sizes depending on where they're going to be applied, and we can apply the HFCT to cable earth sheath. We also apply the HFCT around the core of the cable, and I'll explain why next. So in this example, I've put the HFCT on the earth sheath here, but you could also install the HFCT around the core of a cable there. But importantly, the HFCT needs to be installed on one or the other. It cannot be installed in a place where you're capturing both. The reason is, when a PD occurs on an underground cable, what you'll find is the PD will be induced on the core and also on the earth. So you get equal and opposite signals being induced on both parts of the system, if you like. So what it means is if we put a sensor here, for example, we would be surrounding the earth and the core and we won't detect any signal. That's not incorrect, actually. I should say here we wouldn't detect any signal. So if we install a HFCT on a core, it needs to be a core without the earth, and if we install a HFCT on the earth, it needs to be the earth without the core of the cable. So we need to find a point in the network where we separate the two. So on medium voltage networks like this one here, medium voltage networks tend to be HFCTs are installed in the cable termination. They're installed back in the substation, and quite often they're installed on the earth sheath, particularly for spot testing, because the earthing tends to be more accessible. So that's where HFCTs tend to be installed. You can install them on the core, and in fact on the core you would get a more accurate signal. You'll be able to detect PD a little bit lower if you install it on the core. However, that's not always possible depending on the makeup. A shutdown is required for that installation, so it tends to be on the core when it comes to permanent installation or when it comes to a permanent solution, whereas installing for a temporary application tends to more be focused on the earth sheath as well. Okay, so if we zoom in now to this area of the cable, let's have a look what happens. So again, this is most likely to be in a cable joint, but for simplification, I've took the sort of ideal solution. We've got a single core cable, high voltage cable, and the earth shield around the outside. Now, when a PD occurs, when one of these very small PDs occur during the rising edge of the power cycle, what happens is PD is then induced on the inside of the earth sheath, and also an equal and opposite signal on the outside of the core. So what that means is those two signals, because from the PD source it's emanated away, it's then been induced onto the inside of the earth, the outside of the core. Those two signals are equal and opposite. So if you put a sensor around the cable, you won't detect anything. So that's why we can apply HFCTs around a cable, because we've got those equal and opposite signals inside. Those signals are traveling along the surface. They are trapped inside. They're high frequency signals. They're trapped inside the cable because the cable acts as a Faraday cage, so the signal cannot escape. But what happens is they will, from the PD source, they will travel away from the PD source along the core and along the earth. Now again, I must emphasize these are, with all PD signals, these are high frequency signals, so it's not high current, it's not a load traveling along the cable, it's a high frequency, very fast moving signal. So this high frequency signal is traveling along the inside of the cable, and it will travel. So if my animation works this time, it will travel, there we go, it will travel along the inside of the cable earth in our example, come out at the switchgear and through the HFCT. Now, detecting PD on the earth sheath, the earth must be isolated from the switchgear. If the earth is not isolated from the switchgear, the PD signal will enter the switchgear and be lost. So it's important for the earth to be isolated from the switchgear. Now, when it comes to the lower end of the medium voltage, maybe 11 kV, 10 kV, whatever the standard is in your country, sometimes this may not be the case. Either an installation engineer has made a mistake, or it's not a standard policy to isolate the earth from the switchgear. When we get to the higher voltages, when we get to the HV level and the EHV level, when we're in the hundreds of kVs, obviously the earth is definitely isolated from the switchgear. But in the lower voltage levels, this may not always be the case, and it's always worth checking that situation out before looking to apply this type of technology. If they are directly connected, if the earth is directly connected, what it means is that the HFCT must be installed on the core of the cable. Normally that also means that it must be installed inside the termination. So again, the only place where you can separate the two sometimes is on the core of the cable. Case by case, we look at that with customers, and always happy to help and consult if anybody is in doubt. Now, just a note on EHV. So on extra high voltage circuits, what tends to happen is along the circuit themselves, there is link boxes, there is cross-bonded joint locations. And so what it means is we also have extra opportunities to install HFCT sensors. On top of that, EHV cables tend to be very long. There's quite a long distance, and so what it means is it's quite useful to install at different points, because the typical range of a HFCT is about 4 or 5 kilometers, and so on an EHV circuit that is maybe 15 or 20 kilometers, it's quite nice to be able to install HFCTs along the cable length. Equally, installing sensors along a cable means you get that increased sensitivity. As you would imagine, the smaller PDs are detected more easily, so it is better in EHV applications to install sensors along the actual circuit itself. And the nice thing with EHV, of course, is the earth is separated from the core at these points along the installation. Just another note is they're not necessarily the nicest environments. However, although they're not the nicest environments, we do have solutions for monitoring in these environments. So we can monitor with IP rated enclosures, we can use fiber optic for communication, and we can install underground. Okay, so looking at on the switchgear side, then medium voltage switchgear, what we tend to use is CC-TEV sensors, as we call them, capacitively coupled sensors. Essentially, they're also more commonly known as just TEV sensors. Many of you will be familiar with TEV devices. Handheld TEV devices have been used in the industry for many, many years. And in fact, many companies, that is their only familiarity with, many engineers, that's their only familiarity with handheld, with PD test equipment, if you like. So PD test equipment, the TV sensors are often built inside, so like this one here. So the head of the sensor is a TEV sensor, but also you can get them in external individual sensor types, which is what we use on our permanent monitoring systems. The sensors themselves are relatively simple. They're a capacitor. So one side of the capacitor is the sensor and the other side is the switchgear. And so if you get these high frequency signals occurring across the surface of the switchgear, these capacitive, these CC-TEV sensors will be able to detect this signal. So what happens is, very similar to cable PD actually, just in a different enclosure, a different environment. When PD occurs in a high voltage component, again the signal will dissipate from the source, and it will be induced on the inside of the panels within the switchgear. So on the inside of different panels, and then it will travel away from the PD source. So again, just like cables, it's trapped inside, it's traveling along the surface. And what happens is it comes out through the gaps in the panels. So where two panels are attached together, it travels out through the gaps and along the outer surface of the equipment. So it travels along the outer surface of the equipment, and then it travels across the surface of the TEV sensor, be that either built into, like I said, built into an instrument or physically attached. And then that signal is induced on the sensor. So what it looks like with my, if I just flip through. So what it looks like, a PD will occur in any component of the switchgear, remember, anywhere where the installation may be, the insulation may be weak or damaged, will occur, and then travel along the surface of the equipment, out through the gaps, and out across the front surface of the sensor. The PD travels in all directions away from the PD source, and actually on TEV, the TEV signal, so the cable, like I said, it travels about 4 or 5 kilometers. The TEV signal is a much higher frequency signal because we're a bit closer to the PD. So the TEV signal will typically travel about 4 or 5 meters, after which it will attenuate down to 0. So what it means is when you're detecting PD on switchgear, you're most likely to see it on many panels across the switchgear surface. So here's another one of my fantastic animations. So out from the gaps in the panel and being induced across the surface of the TEV. Out from the gap and induced across the surface of the TEV. Now, it must be noted that PD, again, will travel in all directions away. It'll travel across the surface, across many panels. And so just because you're detecting the PD on one single panel does not necessarily mean that's the source of the PD. And I'll come on a little bit later on how we would attempt to locate those things. The next one then is the ultrasonic sensor. Ultrasonic sensors ultrasonic detection on switchgear is very simple. It's a 40 kilohertz microphone, one of the most simple sensors that you can create, that you can make. Also, the interpretation and the detection of the signal is also very simple. Quite often you use them built into the head of handheld instruments, put some headphones on and point at where there may be some surface tracking occurring. If surface tracking does occur, the sensor is very, very sensitive and will very easily pick up that signal. So we have sensors for permanent monitoring systems, and we also have sensors that we build into the head of devices, like in this next image. So built into the head of devices to pick up the PD. Now, modern switchgear tends to be more enclosed, so the locations that we can apply our technology, the locations where we can apply our ultrasonic sensors, can be more limited. However, where they can be applied, it's very, very sensitive. What we tend to do now with permanent installations is we'll install the sensors inside the cable termination. So it's quite common for us now to look to take a shutdown, to install the sensor very safely, run a connector outside so that in future you can use portable equipment to test or connect it to a permanent monitoring system as well. Here's another animation. Ultrasonic sensors are very directional, it must be noted. So they generally have a field of view of about 30 degrees. And so they're good for about 2 or 3 meters, and they're very directional. So the nice thing about ultrasonic is your location is conducted at the same time as your testing, if you like. So as you swing the device around, you're pinpointing the location as well. This picture on the left is actually quite a nice picture. It shows another type of partial discharge that can occur. This is not caused by, well, I suppose to a certain extent it is caused by weak insulation. But the main problem here is what's happened is the 3 phases are coming inside the termination. The insulation has been stripped back, but the insulation has been stripped back a little bit too early, if you like, and the phases are too close together. So what we've got here is these 2 phases with, this is where the insulation is ending. Some of the insulation is ending. So the very thin insulation here, and the phases are too close together. And so you get this discharge occurring between them. Now, of course, visually we can see this, but before it was visual, the ultrasonic sensor would be able to pick it up. Okay, the final sensor type I want to talk about then is UHF sensors, ultra high frequency sensors. So the application of UHF tends to focus on EHV GIS, and so the problem there is GIS is completely sealed, and so the only signals that escape from GIS are very high frequency, so ultra high frequency, and so naturally we use ultra high frequency sensors to detect the PD inside the GIS. What we use is, if I go to the next one, so our sensors are, typically they're 500 meg up to 1.5 gigahertz, but they could be even more. Actually, IPEC sensors are about 300 meg up to about 2 gigahertz, and we install them on the barriers. So where the 2 components or 2 compartments of the GIS, where they meet, there'll be a barrier in between, and we install the UHF sensor there. That's where we're going to see this ultra high frequency signal, which is going to escape from within the GIS. Quite often, there's lots of different barriers around the equipment, so quite often we install them where the customers have the main concern. So sometimes the main concern is in the CT or the VT or the circuit breaker. Depends on the switchgear, depends on the history of failures of that type of switchgear. Quite often it's also on the cable termination. Cable terminations are naturally a weak point in any equipment. So I think this picture here is a cable termination, so installed on the barrier of the cable termination there. Okay, so with that in mind, IPEC's product range then, what I'm going to go through is I'm going to go through the individual products now. I'm conscious of the time, so I'll try and do this in about sort of 15 to 20 minutes, and then I'll try and stick to an hour and a half. So I'll go through the individual systems and what type of sensors that they have. But again, it must be noted that all the different sensors that I've shown you there are used with different equipment, and then it's all about how that equipment interprets the data, how that equipment processes the data, which is important, not the actual sensor. So one note is which I thought I'd leave till after the sensors are done, is how online PD fits into this whole condition-based maintenance plan, the condition-based maintenance structure you may have in your own organization. So one funny thing about online PD is that currently there's no international standards, if you like, for a lot of online PD testing and monitoring solutions. So there is some very defined standards for offline PD. There's very defined standards for other CBM, such as DGA, gas analysis, for example, tan delta, lots of different other methods of measuring the condition, temperature monitoring of cable circuits, for example. Online PD doesn't have a standard, but it is very useful to combine within your CBM. Traditionally, customers think that because of the name, I suppose, online PD versus offline PD, which is better. Actually, you cannot compete the two together like that. Offline PD has its own unique characteristics and its own advantages and, of course, disadvantages. Same with online PD. It has its own advantages and disadvantages, and it equally should be viewed the same with other types of CBM, other types of condition-based maintenance. Some types of CBM will detect problems before online PD would. Offline PD may detect problems before online PD would, and vice versa. One of the biggest advantages of online PD, of course, is you're viewing the condition of the network live. So that brings two main advantages. One is if you see a PD, you know that it's occurring live. Whereas if you was to do an offline PD test, possibly you would create the PD yourself through the test, or you would only find a future problem, not a current problem. The other side of that advantage is that with online PD, of course, you're conducting the test live. So the asset is in normal operation. You're not taking any interruption and outage. So when you're conducting your test, it's very easy to conduct tests and survey of all your equipment without taking interruptions, without causing customers some temporary outage whilst you conduct the test. That tends to be the biggest advantage of online PD. However, IPEC is of the philosophy that you shouldn't necessarily drop all tests and only use online PD. A combination is the most appropriate. And so what some customers do, for example, so if I take Hong Kong, for example, where they have many of our PD monitoring systems, they use our online PD to monitor 24 hours a day, 7 days a week, so they can always see a baseline condition of their equipment. If they find a particular problem, they can then do an online PD location, and then also they can then take a shutdown and do an offline PD test. So if you like, that's a combination of existing standards which each back each other up. Conducting an offline PD test of 1,300 cables on Hong Kong Island is quite onerous, whereas using a combination of test is perfect. So what we spend a lot of time doing is working with our end users, talking about the advantages you can get from different online PD products, whether it's portable systems or permanent monitors, and discussing how that fits into their asset management program or their CBM program. So for example, maybe you conduct online PD test, online PD location, offline PD test, and a repair. Maybe you conduct an online PD test, then immediately followed by an offline PD test. Then possibly coming back to online for monitoring, then conducting a repair. Or maybe you conduct an offline test, then an online monitoring, then an offline test, then a repair. So all those are lots of different examples of how you're combining offline and online PD together. But the truth is there is no one solution that fits all. And so a lot of our time we work with our customers and we help find that sort of best combination of solutions. Okay, so in terms of our product range then, our instrumentation side, we have the PDSGS, the PD detector, and the PDSG1. The PDSGS and the PD detector are the same in the sense that they use the same types of sensors, the TEV and the ultrasonic, also using a HFCT and the UHF. They both have active PD and noise differentiation. So built into them, the system will automatically look at the power cycle, look at the signal it's receiving, and actively on the screen give you a reading of PD level and noise level. Now that's quite unique in terms of handheld PD instruments, quite a unique thing to do, to give those two separate readings together. They also give you the PRPD, so that phase resolved partial discharge you can view on both devices as well. The main difference is that the PD detector enables you to, as well as doing a quick spot test and looking at the screen, you can also connect it to a device, a mobile device, iPhone, iOS or Android. You can bring the data onto that device and save the data against specific assets in a substation and specific equipment as well. The PDSG1, on the other hand, is mainly focused on switchgear. It also has the functionality of that detection, like the other two devices, but it's also there for location. So using the two sensor channels we provide with the equipment, you have two sensors, and when you place it onto the switchgear, as I mentioned before, that TEV signal, that TEV signal, is traveling across the surface of the equipment. So using your two sensors, the system will give you a precedence. It will tell you which sensor detected the PD first. What that means is you can move along the switchgear and you can pinpoint the PD to a particular panel and usually to a particular component. The resolution between these two sensors is 240 picoseconds, which is the equivalent of about 8 centimeters at the speed of light. So these TEV signals can be accurately located to about 8 centimeters, which is the most accurate location device available. So I'm not going to go into too much detail about what's included in the actual kits themselves, but basically, obviously, The main version of the equipment is focused on medium voltage switchgear, so as standard we provide the sensors and the accessories for the medium voltage switchgear. Inside the device is built in the TV and the ultrasonic, and it's an optional accessory to add on the HFCT for the cables and also the UHF for the GIS. Many customers use handheld devices on medium voltage switchgear, so we don't want to provide the additional sensors at an additional cost, so that's why we have them as an option. The PD detector, similar package, comes with the main sensors we've got, but the main addition is its ability to link to that mobile phone and record the data. Now, when you've recorded data onto a mobile device, you've got two options. You can use the Windows software we provide with the device, so you can analyze the data on a computer. Alternatively, you can share it with the cloud, so you can use the IPEC cloud service. And what that means, if many of your engineers in your network are using the handheld devices, it means that you can record data in your substations and then synchronize and then go home. And the next day, another engineer can go into that same substation with his own device or her own device and then conduct a test in that substation, receiving the data that you recorded the day before. So it means you've got a continuity of testing across all of your engineers. The PDSG1 then, the main application of the PDSG1, like I said, is the pinpointing and the location. It comes with a variety of sensors. It comes with a HFCT, comes with a flexible ultrasonic for a bit further reaching, and it comes with different, than the standard equipment you would expect. It must be noted, actually, now I mentioned the flexible ultrasonic, along with our equipment, we do also provide alternative ultrasonic sensors as well as optional accessories. So many customers may want a parabolic dish so they can detect ultrasonic on a much further distance. We can provide that. And also flexible probes, we have that for the hard to reach areas. And they're compatible with our whole range of instruments. I will put that slide back on, actually. The permanent monitoring systems are applicable across the network, basically, from transmission, primary distribution, and secondary distribution as well. So our equipment is applicable across the whole range. We have installations ranging from 3.3 kV actually, which is a little bit too low, but that's another comment. Right from the low end of the medium voltage all the way up to EHV level, I think 345 kV. We've also done 500 kV testing before as well. So we monitor the full range and all different switchgear and cable components within those ranges as well. Okay, so the two sides to our monitoring really. On the left-hand side, we have the PD alarm. The PD alarm was designed to address the need that customers had to essentially replicate what you're doing with the portable handheld equipment and put it into a small, simple, not expensive monitoring system. And that's what the PD alarm does. So it's switchgear focused. And so if you find a problem with a handheld equipment, you can very quickly install the PD alarm. You can receive the same level of complexity. You get the PRPD, you get that differentiation, and you can also see the data remotely, either from a tablet or on your computer if it connects to a server. So that's the other advantage of the PD alarm. Very simple to install, very small device. The other application of it, which tends to be quite common, is using the PD alarm on small ring main unit substations. So these small RMUs, these very small distributed substations, which normally installing a full monitoring system wouldn't be cost effective. It's a much simpler device to install and use as well. Okay. On the right hand side here, the main range I'm looking at here now is our permanent monitoring systems. It's our what we now call the ASM series. So they did have a couple more names. Originally we separated the EHV from the medium voltage, but ultimately we brought them back together this year because the fundamental principle of operation of the equipment is identical across the range. So although the individual components are different shapes and sizes and different design, the operation in terms of how we acquire the data, how we process the data, and how we display the data to the customer is the same across the board. So we've now brought them together in the ASM series range. So our systems have, anything from 4 channels, 20 channels, up to 128 channels, which means depending if your monitoring point is it's very large, like a primary substation, we can have a monitor with 128 different sensor channels, or it could be very small, requiring just a small 4-channel IP-rated enclosure, say an underground cable joint, or maybe an outdoor termination, like in this case. So we can do a variety of solutions. However, the fundamental principle is the same. If you connect 128 sensors to the system, what we will do is we will acquire the signals at 100 megasamples per second, 14-bit resolution. So extremely high resolution data acquisition. 100 megasamples per second is equivalent to, in one power cycle, having 2 million data points. So that's how much information we have on a single power cycle, 2 million data points. And that is why we're able to fully automate the noise rejection and analysis. So that's why, again, I said IPEC system can operate completely standalone, and it's because we have quite advanced systems to differentiate PD from background noise. And I'll come on to how they work in a moment. Continuous monitoring, so they're all designed for 24/7 monitoring of your assets, and then allows you for remote analysis and PD investigation as well. All of our monitoring systems are compatible with all of our sensors, so we can use TEV, ultrasonic, HFCT, or UHF sensors as well. And then this final sensor on the right-hand side is a temperature, humidity sensor. We also measure the temperature and humidity of the environment, and that's very useful to compare that with PD data to see if there's any correlation of that. Okay, so what I wanted to go through now is just a little bit of a quick step-by-step of how the permanent monitoring works to give you more information on that. And then after that, I'm open to take any questions. So this will be about another 5 or 10 minutes. I'll try and keep it swift. So like I said, our monitoring systems work with all the sensors. They come in different shapes and sizes depending on the application, from 4 channels up to 128 channels, depending on the requirement of the end user, essentially depending on the requirement of the substation, both physical requirement, how many panels we need to monitor, how many cables we need to monitor, but then also environmental requirements. So if it's a very industrialized environment, we have monitoring systems that are more industrial than others. So monitoring systems that can handle higher temperatures, can handle harsh environments as well. Now the way it works is there's two main stages, if you like, or stepped phases of our processing of data. The first one is that digitization side of things. It's that, So the first one is that digitization side of things. It's that acquisition of data, 100 megasamples per second, 14-bit resolution, and of course a range of surge protection and amplification of signals, calibration of signals, before it goes into the monitoring device. Then it's digitized at 100 megasamples, 14-bit resolution, and then it goes into phase 2, which is essentially our decipher system. It's our decipher algorithm, which is what is used to differentiate PD from background noise. So that's in 2 stages. So the first stage is wavelet analysis. So wavelet analysis is highly regarded as one of the best ways to process these types of signals. So let's remember these PDs are very, very low in energy, very small signals, and the background noise is likely to be very large. What happens is, as these small signals are detected by the sensor, along with a whole host of large background noise. Using a wavelet analysis, what we're able to do is take that data and essentially pick out these small PD signals in that much higher background noise, because wavelets, compared to something like an FFT, a fast Fourier transform, an FFT will take a chunk of data and bit by bit take a chunk and analyze it and look for the frequency characteristics within that data, and then if anything's different, maybe reject most of it and then pick out something different in the hope that that is PD. The problem is when you do that, when you do an FFT, when you transform that data, you lose the time element. You don't know where that PD signal is. And so running an FFT means you lose the accuracy of PD detection. You lose your ability to show that PD to the user, if you like. You lose the ability to record that PD. A wavelet analysis is a time and frequency based analysis. So what it means is, as the system is processing the data, it is preserving that time-based analysis at the same time as analysing the frequency changes in the signal. So what it means is that it's looking at the time and frequency domain, progressively assessing the signals, and so you get very large background noise, you get these very small PDs, and the system is very effective at picking out these small PDs, and it can preserve that data, preserve that information of the PD. After it's grabbed that small PD, it then passes it on to our knowledge rules, and basically our PD knowledge rules are what we formed over the past 22 years. So if you remember, we installed our first PD monitor in 1998, and so for the past 22 years we've got this wealth of knowledge, this wealth of information, and so we can analyze individual PD segments, individual PD wave shapes to add that additional analysis of whether we believe this is PD or background noise. So to summarize so PD sensors, 100 megasamples per second, 14-bit resolution. Here's an example of a very noisy input, and we can see there's a little peak here and a little peak here. And the output of the wavelet analysis, it's able to spot these small peaks and essentially pass them over to the next stage of analysis, which would be the knowledge rules. Because we've acquired data at 100 megasamples per second, 14-bit resolution, it means even for the smallest PDs, we're able to measure the rise time, the fall time, the pulse width, the pulse height. So lots of different characteristics about that PD, which aids in our conclusion and our analysis of the PD signal itself. It aids us in making a decision as to whether we believe that really is a PD source or not. So what it means is our system is completely automated in terms of the data processing. It's got lots of characteristics about the PD. It also has the power cycle pattern, the phase resolved partial discharge, and all that information is stored, automatically processed and stored by the ASM. With that data, we then display that data to the end user, and so what it means is that even if the system, or rather when the system is alarming and saying we've got PD on this asset, the data is available for customers to look at the signal and look for problems, rather verify that the system has made the correct conclusion, the correct decision. So because our system is completely automated, we don't require connection to IPEC, so you don't need to send the data to IPEC in Manchester for analysis or secondary analysis. The data can just be inside the substation. So next to the ASM, you could have a screen and you can view the data inside the substation. You could connect it to your private network, your customer network. So the data is available only on your network and completely isolated from the outside world, so for good security. Alternatively, the data can go to the cloud and to IPEC's data server in Manchester. So there's three options there, depending on your IT requirements and depending on your requirements for service. So some customers like the data coming to IPEC because they want IPEC to do the analysis and the reporting. Absolutely fine. Alternatively, we can give the customer some training and leave them to do it themselves as well. So depending on how it's hosted, depends on whether you see it in the substation, on your local network, or on the web. With each monitoring system, we have a small server, or rather with each monitoring network, we have a server, and that server hosts the data for the customers. So there's no sort of individual PC software required. You access it via a browser. So even if that's on your local network, you just enter the correct IP address and you can open the data there. So it doesn't need the internet to operate, but it is a browser-based software. Okay, so data analysis. The system will automatically generate what we call a criticality. So we understand that we have quite complex data on our system. So we're measuring the PD magnitude, we're measuring the PD count, we're measuring the energy, we're monitoring lots of different variables and characteristics. Now the problem is if we plot any one of those characteristics, it's difficult for customers to interpret which one is more concerning. Is it more concerning to have a high magnitude and a low count? Is it more concerning to have a high count, number of PDs, but a low magnitude? So what we've done is we've created a criticality algorithm, refined over the years. Basically what that does is it looks at all the data it has available and it makes a decision on a criticality score between 0 and 100. What that enables our customers to do, because of course we have many customers, we're not looking at one asset or two assets, many customers where we're looking at thousands of cables, thousands of switchgear simultaneously. And so the criticality algorithm, what it does is it scores all of the cables in a score between 0 and 100, depending on the severity of signal it sees, and more importantly, depending on the trends of data. So it depends on how the data is changing over time. So for example, if you see a very high PD, it may be very consistent, whereas you may see a low PD that increases very rapidly. And so because this low PD is increasing rapidly, this system will have a higher criticality value, because the PD will look at that and give it a higher value of criticality, so that you as the user will get an appropriate alert, an alarm, or you will see a red asset on your switchgear, on your system, and be able to very quickly address that asset. So changes in trends are very critical to this type of criticality algorithm. The whole aim of this criticality is to make sure that when you log onto your site and you see hundreds of assets or thousands of assets in some of our customers' cases, you're able to very quickly identify where the problems are in that substation, where you need to pay your attention. Okay, the next few slides just give a highlight of the web interface. We do have another video on our YouTube account actually on how it works. We will be updating that soon because we've got quite a lot of new functionality since we uploaded that video a few years ago. But basically you'll see all the data on one interface, and we run that criticality through the network, if you like, so you can very quickly see the red substations, you can see where the problems are, then you can open the individual substation, see the condition of individual assets, again, see where the problems are, and it's like a tree structure. The more you go down, the more data you see. You open the individual asset and you can see that detailed information I mentioned. We have the PD trend, we have the PD count, we have the PRPD, and we have the individual wave shape. And each one of these bits of data you can generate reports on, you can download, you can even download the high resolution data if you want to do your own offline analysis as well. You can manipulate the data, you can zoom in, zoom out, view longer data over time. And this is a nice highlight of the importance of not just looking at PD magnitude. So in spot testing, we look at PD magnitude, we say this is 35 dB, this is bad. In permanent monitoring, we look at trends. We look at trends of different characteristics. So here's the PD magnitude, that stayed the same. On this asset, the count, the number of PDs was low, and then it suddenly increased. So the criticality appropriately would have increased on this asset. And also it's important to note that by judging only on the magnitude would not be a satisfactory solution. In this case, we've had to use another variable as well. So you can zoom in, you can view more data, more graphs, more charts, including raw data, so you can see what the raw background level is. In this case, it's quite dominated by the PD. This is a load pattern. We don't measure the load, but we can import load information from customers. Load is quite useful to combine with PD data. We can see this count has a variation with load. So load and PD are sometimes have a pattern. Sometimes the pattern is inversely proportional, sometimes proportional. So it is important to consider the load and other variables, such as, like I said, the temperature and humidity of the substation as well. You can generate reports, so you can set multiple alerts and alarms, so that from, of course, you can't check the data every day necessarily, so you can create an alert and alarm, email, SMS, so that you can receive an alarm to inform you to look on the website. Multiple users, it's a user-based system, so you customize this website depending on your requirements, but so would each engineer and each user of your organization also do the same. Various reports can be produced, PDF reports, screen-based reports, or CSV downloads as well. If you have our portable system, you can install the system yourself. You do not need IPEC. So to create the system on the website, it's completely fine for a customer to be able to do that themselves. They can install the ASM in a substation, configure the system themselves, and have it working very quickly, completely automated. Okay, so I think that brings to a close the information. I appreciate that might have been, in an hour and 20 minutes, it's quite a lot of information for me to pass across to you. Thank you very much for your time. Hope you learned something, and watch out for new information that we'll be sending through. Thank you.